Hello, my name is Carter, and I will be walking you through my and Henry's final project for modern optics. Together, we chose to investigate optical tweezers, including the construction of such a device and the impact of the z-distance between the plate and the laser focus. Let's begin with a short background on optical tweezers. First innovated by Arthur Ashkin, a worker at Bell Industries, optical tweezers are scientific instruments that use a highly focused laser beam to hold and move microscopic objects in a manner similar to tweezers. Laser light provides an attractive force, typically in the order of piconewtons, causing objects to be trapped. Manipulating the location of the beam allows for the transport of the attracted object. However, this comes with a small catch, that being that the beam can't move very far. The trapped particles themselves are exceptionally small. In this experiment, we are working with 1 micrometer silica beads suspended in water solution. This schematic of an optical tweezer demonstrates how basic optical tweezers can be in nature. Simply put, optical tweezers can be built by focusing a laser beam through a microscope. Dielectric particles, like the silica beads used, are affected by the force of the laser beam when suspended in a solution such as water. Our specific research concerning optical tweezers revolves around the construction of Thorlabs Portable Optical Tweezers Educational Kit. After this is completed, we focus on the question, does the minimum intensity required to trap a particle with a Gaussian laser beam depend on the z-distance between the microscope lens and the side of the suspended solution? It is important to note that we had to reconstruct and build from scratch the optical tweezer, including completing a complete laser alignment and a complete cleaning of the entire kit. Pictured here is the Thorlabs Portable Optical Tweezers Educational Kit. This is the apparatus Henry and I used. Upon first receiving the device, it was already set up, yet it was not working. It required a complete teardown and rebuild. Pictured here is the precise lengths we went to get the device working. Seen in red is everywhere that required realignment. This included the laser, several lenses, several other lenses, and finally a lot of other lenses. Seen in yellow, the laser required a collimation. Seen in green are components of the camera apparatus and lenses that required deep cleaning. Everything in purple required complete disassembly and needed to be put back together, for they were not initially installed correctly. After getting the laser fixed, we had time to finally start focusing on our research question. That being, what is the effect of changing the z-distance between the focus and the slide? Upon thinking about this question, we determined that a larger laser focus would diffuse intensity with less force acting on the particle, but due to the larger diameter, it would more likely trap a particle. A smaller laser focus has a much stronger and more focused intensity, with more force acting on particles, but a smaller range of impact of the force, so less likely to fully trap a particle and more likely just to push particles around. With this in mind, we predicted that there would be a parabolic-shaped correlation betwixt minimum intensity and beam diameter. Essentially, there would be a sweet spot in z-distance where the beam is wide enough to fully trap particles but small enough to not diffuse intensity. This slide has been prepared with a 1 micrometer solution and is placed under the laser focus. The light underneath the slide is being turned on. Motors controlling movement of the X and Y axes are turned on. This is the laser turning on. Once there is an established output, it should be visible to the naked eye. Adjusting the Z position of the slide in order to bring it into focus to be seen with the camera. Using these dials, the laser beam itself can be moved within the camera's viewpoint. Pictured here is a captured particle being moved by the laser beam. The diameter is wide enough to capture the laser beam, but small enough so that the intensity still has a great enough force to act upon the particle. Here is Henry hard at work setting up our experiment the day we collected results. As we change the axis, you can watch as the laser grows and shrinks as the beads move in and out of focus. Turning off the light, we can see what the ultimate impact of changing the z-distance is on laser beam intensity and diameter. Henry, hard at work taking measurements, determined this pattern of intensity versus beam diameter, which fits our predictions. Our conclusions, beyond that the original apparatus of the laser was flawed and needed complete reconstruction, is that the z-distance matters when attempting to utilize the minimum intensity to trap particles. There is, in fact, a sweet spot wherein the intensity of the laser is focused enough yet wide enough to capture a particle. We believe that further research can go towards arithmetically calculating the ideal z-distance on this particular optical tweezer apparatus, as well as the ideal focused laser diameter to bead diameter ratio, as we hypothesize that there's a sweet spot in this ratio. I will let Henry now have the final word.
I love optics.